Okay, Chapter 10, Section 2, Calculus with Parametric Curves. In this section, we're going to explore how to apply some of our calculus techniques to parametric equations, beginning with tangents. Suppose f and g are differentiable functions and that we want to find the tangent line at a point on the parametric curve x equals to f of t comma y equals to g of t, where y is also a differential function of x. Then the chain rule gives the following. dy dt equals dy dx times dx dt. Remember that we can envision this as maybe the dx is canceling, like that. And that's why dy over dt is equal to dy dx times dx dt. Okay. Now, if we want to find this guy, we want to find dy dx, what we can do is we can divide both sides of this equation by the dx dt. So let's come over here, let's make it green. So we want to divide this side by dx dt, divide this side by dx dt, and then that'll solve for dy dx, right? On the right-hand side, this cancels with that, and then we're just left with this division of dy dt divided by dx dt equals dy dx. Okay, so we can turn that around and rewrite it like this. dy dx is equal to a giant fraction where we have a dy dt divided by a dx dt. Okay, we can organize this in the following. So if dx dt does not equal to 0, then we can solve for dy dx as we did. So dy dx is equal to dy dt divided by dx dt if dx dt does not equal to 0. Okay, equation 1. So we can remember this as thinking of canceling the dt's as well. Right, so we can also envision canceling out this one and this one, same as before. Okay, so this equation enables us to find the slope of dy dt of tangents to a parametric curve without having to eliminate the parameter t. We see from this equation that the curve has a horizontal tangent when dy dt is equal to 0. Remember that horizontal tangents occur when the slope equals to 0. So if we have dx dy dx as equal to this fraction where the numerator is dy dt and the denominator is dx dt, then when the numerator is equal to 0, the dy dt, that's when we'll have the whole fraction will be 0, provided the denominator is not 0, right? So this is when, if this equals to 0 and this is not 0, then we have the whole fraction is going to be equal to 0. And so when the derivative is equal to 0, that's when we have a horizontal asymptote. Good. So horizontal tangent when dy dt equals to 0, provided the dx dt does not equal to 0. And it has a vertical tangent when the opposite happens. When the denominator is equal to 0 and the numerator does not equal to 0, then we have a vertical tangent. Okay. If it happens that both the numerator and denominator equals to 0, then we'd have to find a different technique for figuring out what's going on. Okay, so this is only valid when one is 0 and the other one is not 0. It is also useful to consider the second derivative. The second derivative with respect to x. So this can be found by replacing y by dy dx in this equation. So let me expand this a little bit here. This is the derivative of the first derivative, right? That's what this is. But remember that this derivative is written in t. So when we want to find the derivative with respect to x on dy dx, this is a function in t. A function in t, right? This guy right here. So when we want to find the derivative with respect to x on the function in t, what we really want to do is this. We want to take a derivative with respect to t on this function, dy dx, However, we can't just replace the dx with a dt, so we have to also replace it with, or also include a term of dt dx, right? That way we can envision the dt's canceling, this and this cancel, and that's dx. So this term is this. Good. Okay, so now these we keep together. I'm going to take a derivative with respect to t on dy dx, and then I'm going to separate these a little bit. I'm going to rewrite these as d dt dy dx times, and then I have a dt over dx over here. I just moved it around to the front. And then I'm going to rewrite this as d dt dy dx times, and then for this guy, all I'm going to do, and I'm going to flip it. I'm going to rewrite it as 1 divided by dx dt. Instead of having a derivative of t with respect to x, what I can find is a derivative of x with respect to t, and then flip it underneath 1. Good. Okay, so this last one is exactly this right here. So this is equal to ddt of dy dx divided by dx dt, like this, right? And that's what this describes. The derivative with respect to t of dy dx divided by dx dt. Okay, so remember, this is going to be a function in t, so we can take this derivative, and then we just divide it by dx dt. We'll see it in practice in a little bit. Example 1. A curve C is defined by the parametric equations x equals to 3t squared minus t cubed, comma, y equals to t squared minus 2t. Show that C has two tangent lines at the point 1, comma 2, and find their equations. Number B, find the point on C where the tangent lines are horizontal and vertical. C, determine where the curve is concave upward and downward, and D, sketch the curve. Okay, so to begin with, part A, show that C has two tangent lines at the point 1, comma 2, and find their solutions. So remember, this is 1, comma 2, meaning that x is a 1 and y is a 2. So the first thing we should do is try and figure out what t value exists out there such that when we plug it into this equation, we get a 1, and we plug it into this equation, we get a 2. So let's find that t value. So let's come over here. Show that C has two tangent points at the line 1, comma 2. So that means that the x is equal to 1 and the y is equal to 2 from this right here. So we take our equations, which was x equals to t cubed minus 3t plus 1, and we're going to set that equal to 1. Set x equal to 1. So we have 1 equals to t cubed minus 3t plus 1. And we solve for t. So I'm going to subtract minus 1 minus 1. I end up with 0 equals to t cubed minus 3t. Factoring out t's, we get 0 equals to t squared minus 3. And so we get two solutions. T equals to 0 is one solution, and t squared minus 3 equals to 0 is another solution. So t squared equals to 3, and so t equals to plus or minus root 3. Okay. We can do the same thing for y. Y equals to t squared minus 1. So we set the y equal to a 2, and we should get the same thing. 2t squared minus 1, adding 1 to both sides, plus 1, we end up with 3 equals t squared. And so when we solve, we get plus or minus root 3 equals to t. Okay, so this means that the x coordinate is equal to 1 at 3 different points, at 0 and at plus or minus root 3. On the other hand, y is equal to 2 at 2 different points, at plus or minus root 3. So this shows me that t equals to, so this means So t equal to root 3, well, plus or minus root 3, leads to the point of interest, point 1, comma 2. On the other hand, when t equals to 0, we have x equaling to 1, right? If we put in a 0 in here, that would become x equals to 0 cubed minus 3 times 0 plus 1. So that just becomes 1. And when we plug in t equals to 0 for y equals to 0 squared minus 1, we get y equals to minus 1. So this leads to a different point. Point 1, comma, minus 1. Okay, so that one is not a point of interest. We are told to find the tangents at this point, not this point. So here it is. When t equals to plus or minus root 3, we have our point 1, comma 2. So let's find the tangents and the equations of those tangents at this point. Okay, so now to find the equation of the tangents at that point, let's begin by finding the derivative. So remember, our formula for finding the derivative, dy dx, is equal to this fraction, where we have to find dy dt, and then divide that by dx dt. So let's find them separately and then divide them. So dx dt is equal to the derivative with respect to t on t cubed minus 3t plus 1. And so this derivative, dx dt, is equal to 3t squared minus 3. And likewise, dy dt is equal to the derivative with respect to the letter t on t squared minus 1, which therefore dy dt is equal to 2t. Okay, so now we can bring that together and find dy dx as equal to the 2t, that's the dy dt, divided by 3t squared minus 3. Okay, so here is our derivative. And now we can use that to figure out what's happening at our points of interest, which was plus or minus root 3. So at t equals to root 3, we've established that this results in a point, an ordered pair point on our graph, which is going to be the point 1, comma 2. But now let's find the derivative at that point. So dy dx is going to be equal to 2 times root 3 divided by 3 times root 3 squared minus 3. So now this becomes dy dx is equal to 2 root 3 divided by 3 times 3 makes it 9, minus 3 makes it 6, and then they reduce to give you that dy dx is equal to root 3 divided by 3. And then we get a very similar result when we do the minus. Let's scoot it over here. So now at t equals to minus root 3, we end up with dy dx is equal to 2 times negative root 3 all over 3 times negative root 3 squared minus 3, which then gives us dy dx is equal to minus 2 root 3 divided by 9 minus 3 again gives us a 6. So we just get negative root 3 over 3. Okay. All right, so now to find the equation, we just use our point and our slope. So slope being equal to root 3 over 3 at point 1, comma 2, we end up with y minus 2 is equal to root 3 over 3 x minus 1. So if we just simplify for y, we get that y equals to root 3 over 3 x minus root 3 over 3 plus 2. And then likewise over here, if we want to use slope equal to negative root 3 over 3 at 0.1 comma 2, we end up with y minus 2 is equal to negative root 3 over 3 x minus 1 minus 1. And so y equals to negative root 3 over 3 x plus root 3 over 3 plus 2. Okay, so here are our two equations of our tangent lines. This one and this one. Okay, so let's use Desmos to graph the whole thing and see where our ordered pairs are so far, and that these equations really are the tangents at those points. Okay, so using Desmos, let's graph our function. To do that, we're going to come over here and type in our equation in t to the power of 3 minus 3t plus 1, comma, t squared t to the second power minus 1. That's it. And then let's make sure that we range t through a cycle that's big enough to see the whole picture. And so we see something like that. Okay, so here's our whole picture. Let's evaluate this at a particular point. So let's come over here and let's make this the letter A. Let's make A a slider and get A to the second power minus 1. Okay, so here we have the little ordered pair. You can see what's going on at various points of t. So I'm using t to be a specific point on here. But anyway, as we slide this is really the value of t, we can see where it's going. So when we start with negative 10, oops, off the grid. So it looks like we only have, okay, there we go. So starting at like negative 2.2, there it is, at 2, sliding that way, we can see we crossed this point right there, this cross. And then we keep going and curves this way and goes around, and then it crosses it again. So it crosses this point twice, and that is the point 1 comma 2. Let's graph it, 1 comma 2. Here it is. So it crosses it twice. It crosses it once right around here, and then we go around this loop, and then eventually it'll come back and cross it again right around there. So this first one should correspond to our first t value, which was negative root 3. And then the second one should correspond to positive root 3 when it crosses it over a second time. We can confirm that by just plugging in these values here. So if we plug in a root 3, yep, we get the point exactly right there. And then same thing when we put in a negative root 3. Yep, still at that point right there. Okay, so now let's confirm that our equations are really the tangents at these points. So let's type those in. We had y equals to okay, there we go. So I typed in this equation here, and so we have this tangent line, and then we have this other tangent line, which goes this way. So at negative root 3, the point, the graph crosses this point, 1 comma 2. Remember, it was going in this direction at that point. And so we have a slope going down like this, and the tangent line is right here, this red one. And then as we keep going at positive root 3, we do another lap of this thing. Now we're going up this way. And so now the tangent line is going to be this one. It's got a positive slope going that way. Okay, so those are the two equations of our tangent lines at that point. Okay, part B, find the points on C where the tangent line is horizontal or vertical. Okay, so let's write down our equations. So let's come back over here. So remember that we have that dy dx is equal to dy dt divided by dx dt. Okay, so we have a horizontal asymptote when the whole derivative is equal to 0. So that'll happen when dt dt is equal to 0 and dx dt does not equal to 0. So horizontal tangent when dy dt equals 0 And at the same time, dx dt does not equal 0. Okay, so let's set our own numerator, the dy dt. Now for us, remember that, let's write it down like right here. dy dx for us was equal to 2t divided by 3t squared minus 3. So let's set the numerator, 2t equal to 0. Obviously that means that t equals to 0. And then we just want to confirm that the denominator is not equal to 0. So 3 times 0 squared minus 3, well, that's just going to be equal to minus 3. So not 0, not 0. Okay, so we have a horizontal tangent line at t equals to 0. So let's see what kind of ordered pairs that results in. So our two equations were x equals to t cubed minus 3t plus 1. So this gives us x equals to 0 cubed minus 3 times 0 plus 1, or just x equals to 1. And likewise, y was equal to t squared minus 1. So y equals to 0 squared minus 1. So y equals to minus 1. So we have the ordered pair 1 comma negative 1, and that corresponds to t equals to 0, and that'll give us a horizontal tangent at that point. So when t equals 0, we get the point 1 comma negative 1, and we know we have a horizontal tangent line there. Tangent. Okay, likewise, verticals happen when the opposite is true, when the denominator is 0 and the numerator is not 0. So we need to figure out dx dt equals 0, but at the same time, dy dt does not equal to 0. So find all the t values that make the denominator equal to 0, and at the same time confirm that the numerator is not going to be 0 at those points. So the denominator being 3t squared minus 3, set that equal to 0, solve for t, we get 3t squared equals 3, t squared equals to 1, so therefore t equals to plus or minus 1. And now at t equals to 1, the numerator is 2t, so 2, 1 equals 2, not 0, not 0. And then 2 times minus 1 is also obviously equal to minus 2, not 0. So we have two vertical asymptotes at t equals to 1 and t equals to negative 1. So at t equals to negative 1, we end up with x ordered pair value of 1 cubed minus 3 times, minus 1. So let's make this minus 1 there, plus 1. So x equals to minus 1 plus 3 plus 1. So x equals to 3 is the ordered pair. And at t equals to positive 1, we end up with x equals to 1 cubed minus 3 times 1 plus 1, which gives you x equals to 1 minus 3 plus 1, which gives you 2 minus 3 gives you negative 1, and then the corresponding y value, y equals to t squared, so minus 1 squared minus 1, which gives you 0. And over here we end up with y equals to positive 1 squared minus 1, which is also going to be 0. So this leads to the ordered pairs 3 comma 0. And then over here we end up with the ordered pair negative 1 comma 0. And so we have vertical asymptotes at these 2 points. Vertical tangent at points 3 comma 0 comma 3 comma 0 and negative 1 comma 0. Okay, let's confirm that with our graph. So let's graph all those ordered pairs. We had negative 1 comma 0. Here it is. We can see we're going to have a vertical asymptote there, vertical tangent line. Same thing with 3 comma 0. That's point there, this point there, this point there. So here and here we have 2 vertical asymptotes, and then we also have the point 1 comma negative 1. Which is this point here. So clearly we have a horizontal tangent line here vertical asymptote here and a vertical asymptote here, which then correspond to the lines y equals to -1 as the tangent line, which is horizontal right here at the point 1 comma -1. And for the vertical lines, we would type in x equals to -1 and x equals to +3. Put them all in the same color. How about orange? Let's make them all orange, 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 and done. And okay, let's get rid of these tangents. It's too busy. There we go. So we have this line right here, which is horizontal at 1 comma -1. We have this line here at -1 comma 0, which is vertical, and same thing here at 3 comma 0. Okay, so this is what we have so far. Let me zoom out. We found our first derivative was equal to 2t all over 3t squared minus 3. We found the equations of the tangent lines at the point 1 comma 2. And now we found the places where we have horizontal and vertical tangent points. So let's move on to part C. Okay, part C, determine where the curve is concave upward or downward. To do that, we need to find the second derivative. So recall that our formula for the second derivative was this. Second derivative of y dx squared is equal to the derivative with respect to t on the first derivative, dy dx, divided by dx dt. So we got to find a derivative of the first derivative with respect to t and then divide the whole thing by dx dt. And for us, let's write down the dy dx again. We found this to be equal to 2t divided by 3t squared minus 3. Okay, so let's find the derivative. So that means that d squared y over dx squared is going to be equal to the derivative with respect to t on 2t divided by 3t squared minus 3, and then the whole thing gets divided by the dx dt, which is just going to be equal to the 3t squared minus 3. Okay, so just focusing on this numerator up here, that's just going to be a quotient rule. So let's expand that whole thing out. dy dx squared is going to be equal to low d high minus high d low all over the denominator squared we go. 3t squared minus 3 squared. Okay, so right now I'm just focusing on this numerator, applying the quotient rule to this, low d high minus high d low over the denominator squared we go, and that's where this comes in. So I still have to find the derivative of this and the derivative of this, and then simplify it after that. And then the whole thing still gets divided by the dx dt term, which is 3t squared minus 3. Okay, so this turns into a 2, and this turns into a 6t. Let's simplify this. This becomes t divided by t squared is equal to 3t squared minus 3 times 2 minus 2t, and this becomes 6t divided by 3t squared minus 3 squared. And now we have a giant fraction here where what I could do is think about this as a little fraction as well. So we have one giant fraction here where we have a fraction in the numerator divided by another fraction in the denominator. So we can multiply the numerator times the reciprocal of the denominator. So I just end up flipping these upside down and get 1 over 3t squared minus 3, which can of course be combined with this one, power 2, power 1, that becomes power 3. So let's combine all that. X squared becomes 6t squared minus 6 minus 12t squared divided by 3t squared minus 3 power 3. So then this gives me minus 6t squared minus 6 divided by 3t squared minus 3 power 3. And then of course I can factor out a minus 6 from the numerator, and that basically gives me my answer. I'll put it over here. The second derivative with respect to x becomes a minus 6 t squared plus 1 divided by this 3t squared minus 3 power 3. Okay, so to establish concavity, we need to figure out when that second derivative is positive, when that second derivative is negative. And so to do that, we have to break this down in pieces. Now the numerator, if we just focus on the numerator alone, no matter what value of t you choose, the answer is always going to be negative, right? Because plus or minus t, any value squared becomes positive, plus 1 is still positive, times a minus, a negative 6, becomes negative. So the numerator is always negative, no matter what value of t you choose. So the denominator, well, that's where we need to work. We need to figure out what values of t result in a positive, what values of t result in a negative. So we should first figure out when it equals to 0, and then break it down from there. So let's set this part equal to 0. This is a little bit of separate work here. So we're going to take 3t squared minus 3, set it equal to 0. 3t squared equals 3. T squared equals 1. So we get t equals to plus or minus root 1, or just plus or minus 1. T equals to plus or minus 1. Okay, so those are the two values that will result in a 0 here. Okay, so now we can figure out the zones that are separated by those and figure out whether it's going to be positive or negative in those values. So let me zoom out over here, and let's create some number lines. So let's create a number line for just the denominator, which is going to be, well, let's just do this. 3t squared minus 3 cubed for that guy right there. And this is the t-axis. So I know I'm going to have a 0 here, a 1 there, a minus 1 here. I know I get zeros at these points. 0, 0. Okay, what about the other zones? So we have 3 zones to think about. We have this zone we have the zone from negative infinity up to negative 1, and then we have the zone from negative 1 up to positive 1, and then again we have this other zone from 1 out to positive infinity, out to negative infinity, out to positive infinity. So we can just think of test points in these regions to see what happens. So if we pick a test point from over here, let's say t equals to negative 2. This one, obviously 0 is the most obvious test point, t equals to 0. And then over here, how about t equals to positive 2 in this zone over there? And remember, all we really care about is the sign, not necessarily the actual numerical value. So let's see what happens. If we plug in a t equals to negative 2, we get 3 negative 2 squared minus 3, the whole thing raised to the power of 3. That becomes 4 times 3 is 12 minus 3. That's going to be equal to 9 cubed, definitely a positive answer. So here in this zone, we get a positive number. Positive numbers there. What about here? If we plug in a 0, we end up with 3 times 0 squared minus 3 cubed. That becomes 0 minus 3. That's a negative 3 cubed. The cube preserves the sign, so we end up with a negative in this zone, negatives. And then finally, well, the same thing's going to happen when I plug in a 2 as what happened with a negative 2. We'll just end up with a positive number. We're going to get 2 squared minus 3 cubed. That's going to be 4 times 3, 12. We end up with 9 cubed. Should have written that down, negative 3 cubed. And then over here, we ended up with the same thing, 9 cubed. So we end up with positives from negative infinity to negative 1, negatives from negative 1 to 1, and then from 1 to infinity, we end up with positives again. Okay, but that's just the denominator, remembering that the numerator is always negative. We can combine that to give us our final answer. So let's combine that over here. If we have minus 6t squared plus 1, here is negative 1, here is positive 1, and, well, this thing is always negative, so it's going to be negative in this zone. 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 So now, finally, when we think about the division of the two, we have that the derivative d dx squared, which is equal to minus 6t squared plus 1, divided by 3t squared minus 3 raised to the power of 3. So now this derivative is equal to following number line. We have negative 1 and 1. So these are two places where the denominator is 0. Okay, so we're just looking for signs here, so that's not going to be important. But in this zone, from negative infinity up to negative 1, we end up with a positive divided by a negative, or the other way around, a negative divided by a positive. So we end up with a negative. A negative divided by a positive becomes a negative in this zone. And then in the middle zone, we end up with a negative divided by another negative, which ends up giving us a positive. And then finally, in the last zone over here, we end up with the same thing of a negative divided by a positive, which gives us a negative. Negative. Okay, so the second derivative is negative, meaning that the first derivative is decreasing, which means that the whole thing is concave down. So we'll say concave down and concave down as well here. Concave down. And then in the middle, we are concave up. Concave up, right? So this zone is from negative infinity to negative 1, concave down, concave up from negative 1 to 1, and concave down from 1 out to infinity. Okay, so now remember, these are t values. So this is for t being in this value. This is the t-axis. So when t falls in this range, we have concave down. When t falls in this range, we have concave up. And then when t falls in this range, we have concave down. Let's confirm that with our graph again. So let's come back up here. I need to list this as a variable. Okay, so from negative infinity all the way up to negative 1, stop at negative 1 right there. So from negative infinity out to negative 1, this portion of the graph here is concave down, and so is the graph from 1 to infinity. So we'd skip over to 1. Here's 1. Here's 1. So from this portion of the graph out that way, we are also concave down. So from there to there, concave down. From there to there, concave down. And between negative 1 and 1, we have this portion here, which is concave up. Okay, so that matches with our results. Okay, so piecing it all together, we have our graph look like this. We were told about this point 1, 2. So we have this point right here, which was the point 1, 2 is this point right there. So our graph does cross that point at 2 points. We figured out that that happens when t equals to plus or minus root 3. At t equals to 0, we also have another place where x equals to 1, and that would be this one over here. This is when t equals to 0, we have the point 1, negative 1. And we found that we have a horizontal tangent line there. So let's do it in green. Let's do it in red. We have a horizontal tangent line right here at this point. And we have vertical lines at this point over here and at this point over here. Put it in green. So this would be the line y equals negative 1, which is horizontal. Here we end up with the lines x equals to 3 and the line x equals minus 1. We also found the tangent lines at this point, like this, and then there's another tangent line at this point over here going like that. So this one occurs here when t equals to negative root 3, and it's equal to this equation. So this one is y equals to negative root 3 over 3x plus root 3 over 3 plus 2. Whereas this one over here is the other one, y equals to positive root 3 over 3x minus root 3 over 3 plus 2. That would be this equation that goes this way. And remember, this happens when t equals to, this one's when t equals to positive root 3. This one happens when t equals to negative root 3. And then we figured out these values as well for the horizontal and vertical asymptotes. This happens when t equals to 0. And these ones happen when t equals to plus or minus 1. So I think this one was t equals to minus 1, and then this one happens at t equals to positive 1. And then this point right here happens when t equals to plus or minus root 3. T equals to plus or minus root 3. The minus root 3 is when it goes in this direction, and then it comes around and goes again through the same point, 1, 2, when t equals to positive root 3. And then we just established concavity, so everything from here all the way up to here, which is when t equals to negative 1, is this point right there, is going to be concave down. So will the equation or the graph be concave down from this point over here when t equals to positive 1, going this way, it's also concave down. And then in the middle here, from negative 1 to 1, we end up with this portion here, which is going to be concave up. So let's put it here. Concave up in this direction, from here to here. T goes from negative 1 to 1. And then concave down from 1 to infinity, and concave down from negative infinity up to negative 1. Okay, so that finishes everything for this one. Okay, example 2. Find the equation of the tangent to the curve x equals to sine 2t plus cosine t, comma, y equals to cosine 2t minus sine t when t equals to pi. Okay, so the first thing we want to do is think about or calculate the ordered pair x comma y that results when t equals to pi. So let's calculate that. So when t equals pi, we end up with x equals to sine of 2 pi plus cosine of pi. And so x is equal to 0, sine of 2 pi is 0, and cosine of pi is negative 1, so plus negative 1. So we end up with x equals negative 1. And likewise, the y coordinate, y, is going to be equal to cosine of 2 pi minus sine of pi. Cosine of 2 pi is 1 minus sine of pi is 0. So we get y equals to 1. So we have the ordered pair negative 1 comma 1 when t equals to pi. Okay, so we have the ordered pair. Now we need the slope of the tangent line at that point, which means we have to find the derivative. Remember, the derivative is going to be dy dx is equal to dy dt divided by dx dt. So we have to find these two separately and then kind of bring them together to give us this derivative. So let's find dy dt. That's going to be the derivative with respect to t on the function cosine 2t minus sine of t. So dy dt is going to be equal to minus sine 2t times 2 minus cosine of t. And the derivative with respect to t on x, dx dt, is going to be the derivative with respect to t on the sine 2t plus cosine of t. So dx dt is equal to cosine of 2t times a 2 and then minus sine t. Okay, so then bringing it all together, we get that dy dx is equal to minus 2 sine of 2t minus cosine of t, that whole thing divided by positive 2 cosine of 2t minus sine of t. Okay, so now at t equals to pi, we can find our derivative. Our derivative, dy dx, is going to be equal to minus sine of 2 pi minus cosine of pi divided by 2 cosine of, oh, there's an extra 2 here, sorry, minus 2 sine 2 pi minus cosine of pi, following this formula down here. So 2 cosine 2 pi minus sine of pi. Okay, so sine of pi is 0, so we end up with dy dx is going to be equal to minus 2 times 0, sine of 2 pi is 0, minus cosine of pi is minus 1, and then cosine of 2 pi is 1, so we get 2 times 1, minus sine of pi is 0. So dy dx becomes 0 minus minus becomes 1 over 2. So 1/2. So our slope is going to be equal to 1/2 at that point. So now let's find the point. So the point is this guy. So using slope equal to 1/2, point equal to -1 comma 1. This is when t equals to pi. We have this point, this slope, so we can use our formula y minus 1 equals to 1/2 x minus -1, which becomes y minus 1 equals to 1/2 x plus 1. Distributing the half and then bringing the minus 1 over, we get y equals to 1/2 x plus 1/2 plus 1, giving you 2/3, and there's our answer. Y equals to 1/2 x plus 1/2, which is 3 over 2. So this is the equation of our tangent line at point -1 comma 1 when t equals to pi. Okay, all right, so now let's use Desmos to graph all of this and make sure that it all makes sense. Okay, so here in Desmos, we're going to type in our equation. All right, so here's our equation, sine 2t plus cosine t comma cosine 2t minus sine t. Now we have to make sure that we give t enough space to draw out the entire picture. Let's go through, say, minus 10 pi. Okay, I can see that that's going to be already a lot. It completely covers one period of the whole thing. So how about if we just go from -2 pi to positive 2 pi, and let me copy this with a variable. Copy b. So instead of a t, I'm just going to make it a constant value of a, and then we can trace it. Come on, there it is. Okay, so you can see that there's my little dot right there, tracing along this guy here, and the whole thing gets traced out in a period that's smaller than -pi to 2 pi. We can talk more about that, figure out what a whole period is in a different thing. That's not really what we want here. So if we want to go from 0 through, I don't know, 2 pi, 0 to 2 pi. So 0 starts here at this corner. Here's 0 at 1 comma 1. And then as we move forward, it seems to complete one full picture in 2 pi. From 0 to 2 pi will complete one whole period of this whole image. And then if you keep going beyond that, it'll just start repeating itself. So if we go out to 4 pi, it'll do it twice. It'll trace it once right up to there, finishes it once, it does one lap, and then it keeps going, and it'll do another lap after that. So we get to 2 laps if we do go from 0 to 2 pi. Okay, so you just have to, at this point, just give yourself enough range for t to make sure you capture the whole picture. If you notice that when I first typed it in here, it only went from like 0 to 1 by default. That's what it does. And then you'd only get a small portion of the whole picture. Okay, so going from -2 pi to positive 2 pi is a nice standard range for t. And then as we can see, that's going to lap it twice. Okay, so now in particular, we were interested in the point when t was equal to pi. When t is equal to pi, we have this point right over here, which results in the point -1 comma 1. And then we also found the equation of the tangent line at that point, which we found to be equal y equal to 1 divided by 2x plus 3 divided by 2. So let's put it in red. There it is. So here is our point, -1, 1, and here's our tangent line right here, then red at that point, whereas this is the equation. Y equals to 1/2 x plus 3/2. Okay, next let's think about areas. So we know that the area under the curve y equals to f of x from a point A to B is capital A equals to the integral from A to B of capital F of x dx. Remember that I always like to include the variables here when they get a little complicated, so that I remember that this is referring to x equals to A. This is where x equals to A and x equals B, since the variable of integration is an x. Okay, so if the curve is traced out once by a parametric equation, x equals to f of t and y equals to g of t, as t ranges from alpha to beta, then we can calculate the area formula by using the substitution rule for a definite integral as follows. So capital A, the area of interest, is the integral from a to b. Remember, this is as x goes from a, x goes to b, of y dx. So now what we're going to do is we're going to say, well, the y is actually equal to g of t. Remember, this guy is g of t. And to do a substitution and get the dx, we're going to work with this guy. So we have that x equals to f of t. So a derivative with respect to the letter t, since this is a function in t, on both sides gives me this, d dt of f of t. So on the left-hand side, I'm just going to rewrite this as dx dt. And here, well, it's just f prime of t, once we figure that out. And then, of course, now we can solve for dx by rewriting this as dx equals to f prime of t times dt. And then that can be used right here to replace this dx. So this dx becomes f prime of t dt. And now we've completed our substitution. So y dx becomes g of t times f prime of t dt. And now we have to make sure to use the t variable for integration. So this is as t goes from alpha to t goes to beta. Right, so make sure you set up your variables of integration as well. Okay, so the formula is not too bad. It's going to be the y function in t, y equals to g of t, the g of t. And then you take a derivative of the f of t function that represents the x with respect to t. And then that becomes your f of t, integrate with respect to t, and make sure you find your t values for alpha and beta, which cover one whole period of this integration. All right, let's do an example. So for example, find the area of the region enclosed by the loop of the curve x equals to 1 minus t squared, comma, y equals to t minus t cubed. Okay, so the graph is given right here. Let's put this in Desmos ourselves to see how we can recreate this, and then we want to see how we can get this area in blue. So let's go over to Desmos. So we have 1 minus t to the second power, comma, t minus t to the third power, like this. And I'm not sure how big to make the range of t to get this whole picture, so let's just try negative t to negative 10 to positive 10. Okay, so that's what it looks like. Let me zoom in, and there we go. Okay, so this is the same sort of picture, and I want to find the region in here, which goes from there to there. So if t, let's copy this as a constant. So copy, put this over here, and let's make this a constant a slider, a, and a. Okay, so now we can see what happens if I start off at 0 and go off to, say, 10. At 0, I have this point right here, right, which makes sense. 1 minus 0 is 1. And then as I slide forward, I see that I trace out the top half of this at this point. So from here, I can see that it just goes from 0 to 1. Let me change this now from 0 to 1. 1. So just see how the red dot is just tracing the top half of that loop from 0 to 1. So 0 corresponds to this point right here. If I put in a 0, 1 minus 0 squared is 1. And then as I move this way, it traces the top half and gets to there. If I keep going, it's going to continue to go this way. But now I suspect that if I go back into negative 1, see what happens there. I go all the way back beyond that to negative 1. There's the other loop. So from negative 1 to positive 0, from negative 1 to 0, we get the bottom half of the loop. And then from 0 to 1, we get the top half of the loop. Okay, let's confirm that with some arithmetic. Okay, so now in our case, the graph was given, but if the graph wasn't given, then you'd have to use a technology like Desmos or your TI-84 to graph it, and you see the region of interest here, the loop created. Okay, so it's important to point out this point right there, 0, 0, and this point right there, which would be the point 1, 0. So this is when x is equal to 1 and when x is equal to 0. Those are the two important points that will trace this. So let's figure out what t values produce a 0 and what t value produces a 1. So let's work with t here and set it equal to 0. X equals 0 when 1 minus t squared equals 0. And so moving it over, we get 1 equals to t squared. So square root plus or minus 1 equals to t. So t equals to plus or minus 1. So there's going to be 2 points when t equals to 0. 2 points when x will be equal to 0. What about when x equals to 1? X equals to 1 when 1 minus t squared equals 1. So if we subtract 1 from both sides, we get minus t squared equals 0. So t squared equals 0. So t equals to 0. So at t equals to 0, we have this point here. So this point right here is going to be at t equals to 0, right there, which makes sense. We put a 0 in here, 0 squared, 1 minus 0 squared. And we get 1 minus 0 squared. That's going to be equal to 1. And then at this point over here, this happens at 1 and minus 1. So we saw from our Desmos that the graph actually starts getting traced out in this direction. So right when we end up with t equals to minus 1, we're going in this direction like this. So we trace out the bottom part of this little loop from negative 1 to 0. And then from 0 to positive 1, we trace out the top half of the loop. So we end up crossing again the same spot at t equals to 1. Same spot. So this way and comes around. Okay. So from 0 to 1, we trace out this top half. We trace out the top half of this thing here as t goes from 0 to 1. T tracing from 0 to 1 traces out the top half. Now we're interested in the entire region blue here, but keep in mind that when we do our simple integral, let's go back to basic integration, back from like chapter 5, intro to integration. If we're integrating f of x dx from a to b, what this means, it's an area, and just a quick little sketch of what that could look like. If we have some function that does this, f of x, from a to b, then this is the area that's going to be in here. This area right in here. It's going to be the area between a and b, trapped between the x-axis and the function. The x-axis and the function. Okay, so we're going to do the same thing here. We're going to integrate the area between this point and this point that's trapped between our function and the x-axis, and using symmetry we're going to realize that's actually equal to double that. So let's set it up. The area in blue. So the area in blue is going to be equal to this integral. We'll think about the limits in 1 second. And it's going to be following this little formula, g of t times f prime of t dt, where g of t is just the function y equals to g of t. So this is just going to be t minus t cubed, like this. Y equals g of t. I should put that over here just to make sure it's clear. X equals some f of t function, and y equals some g of t function. So this is going to be the g of t function times the minus 2t dt, which is going to be the f prime of t dt. That's this part right here. Okay, so we piece it together, and now we have to think about the limits of integration. Remember that when we traced out this region, we started with values here, and it traced in this direction, and then it ran into this point, and then above, and then back down to this point. So this thing is tracing as t goes from 0 here up to 1. But when we want to do a regular integral, like back over here, we want to integrate from a to b. Integration from a to b starts here and then goes that way in the x increasing direction. So we want to start at 1. T equals to 1 is, t equals to 1 is this point right here, and then going this way would go sort of backwards to t equals to 0. So from t goes from 1 to 0 to trace it out in the regular direction. And then that would only cover the top half, right? So this would be equal to twice that. Okay, so we have our integral. The setup is the hardest part. Then we can just try and solve this. So the area is going to be equal to minus 4 on the outside, minus 4 integral from 1 to 0 of t to the power of 2 minus t to the power of 4 dt. And then remember that if we want to switch the limits of integration, we multiply by an extra term of negative 1. So I'm going to do that. I'm going to rewrite this as the area equals to negative 1 times negative 4 integral from 0 to 1 of t to the second power minus t to the fourth power dt. Okay, so this extra minus 1 comes from flipping the limits of integration, one of our properties of integrals. And the area then becomes positive 4 integral, well, I'll just go ahead and solve the integral. This becomes 1/3 t to the power of 3 minus 1/5 t to the power of 5, evaluated from 0 to 1. So now this just becomes the area is equal to 4 times, and this is going to be 1/3 something cubed minus 1/5 something to the 5th power minus 1/3 something cubed minus 1/5 something to the 5th power, like this, where here we evaluated at 1, here we evaluated at 0. Luckily, this is a really simple one. That's 0. That's 0. This is just going to give me that this area is equal to 4, and this is going to be 1/3 minus 1/5. So we just get a common denominator, which is going to be 15. Multiply this guy by 5 over 5. Multiply this by 3 over 3. So we get 5 over 15 minus 3 over 15. Let's come over here. So the area is equal to 4 times, and this is going to be 5 over 15 minus 3 over 15, which is going to give me 2 over 15. 4 times 2 over 15 is my area. And finally, the area is going to be equal to 8 over 15, and that's my answer. Okay, next let's talk about arc length. Okay, let's go over this like an overview of the theorem. It's not really like a rigorous proof or anything, but we're just kind of walking through the idea of it. It is a little complicated, I'll grant you guys that, but keep in mind that the actual work we do is going to be a lot easier. This is going to give us a pretty easy equation to follow, and we'll be able to do an example afterwards. You'll see it's not that bad. All right, so let's just walk through this explanation of the theorem. So this goes back to section 8.1. We already covered this, so a lot of this is a little bit of review. So we already know how to find the length L of a curve C in the form of y equals to f of x, as x ranges from a to b. Formula 8.1.3 says that if the derivative, capital F, is continuous, then length L is equal to the integral from a to b of the square root of 1 plus dy dx squared dx. So if you recall from chapter 8.1, these questions were very formulaic, right? We found our equation, y equals to some function in x, found its derivative with respect to x, squared it, added 1, took the square root of the whole thing, and then we integrated, and that gave us the length of the whole thing. So now we adapt that to parametric equations. Suppose that c can also be described by the parametric equation x equals to f of t and y equals to g of t, as t ranges from alpha to beta, where dx dt, this is important, where dx dt, which is equal to f prime of t, is always positive, right? Always positive. The rate of change of x with respect to the letter t is always positive, means that x is always increasing, right? The rate of change, the instantaneous rate of change of x is always a positive number, means it's always increasing. So x is always moving forward, right? Not necessarily the value of t, it's just the value of x is always moving forward. This means that c is traversed once, right? It never retraces itself. Remember that parametric equations allow really complicated images, maybe something like this, and it allows things to retrace themselves. So we could have something where we move forward, and then we move backwards, and then we move forward, and then we move backwards, and we move forward, and we move backwards. So it's constantly retracing itself. So parametric equations allow us to do stuff like that, but then we wouldn't get the true length of a curve. So we have to make sure that the derivative dx dt is always positive. This means that c is traversed once from left to right as t increases from alpha to beta. And f of alpha equals to a and f of beta equals to b. Putting this formula into formula 2 up here and using the substitution rule, we get the following. All right, so here we're just copying this down here, and we're going to say that dy dx, we already have from earlier that dy dx is equal to dy dt divided by dx dt. We've already been using this property, right? This is under the knowledge that the parametric equation is defined this way: x equals to f of t and y equals to g of t. So we take the derivative of the y function with respect to t divided by the derivative of the x function with respect to t. So anyway, we just took this and replaced it right here. This becomes this. And now for this guy, you can think of adding a dt and just separating it, right? So it's just a little trick. You can always think of like these guys cancel to just give me dx, which is that dx right there. Good. So this is dx dt. And for the dx over dt, the dx dt term, we just want to use this little idea. Let's put it in green. That dx dt is the same thing as dx dt squared square rooted, right? And this is true because we are working with the idea that dx dt is always positive. So squaring it and square rooting it is going to give you the same result. And then when we do that, then we can stick the dx dt squared inside the root, right? Since they're both a product of two roots. And once you put it inside the root, then you can distribute. And so you end up with this dx dt squared times 1 plus dy dt divided by dx dt squared, and all of that is inside this root. Okay, so when we distribute this dx dt squared, we end up with 1 times dx dt squared. That's how we get this term. And when we multiply this times this one, the denominators cancel, giving you just the numerator, which is dy dt squared. Okay, so that's how we get this, the square root of dx dt squared plus dy dt squared inside the root, and then we integrate with respect to t, that's dt. And so these limits are with respect to t, as when t equals to alpha, that means that we get the a value, x equals to a. And when t equals to beta, then f of b equals to b, so the x is b. So we've changed from x goes from a to x goes to b, and now we've changed it to t goes from alpha to t goes to beta, right? And again, assuming that the dx dt is always positive, then that means that it's not going to retrace itself. X is going to go from a to b without any retracement. Okay, and so this will give us the length of the curve along that space. Okay, so like a little further explanation. So even if c can't be expressed in the form y equals to f of x, this formula, formula 3, is still valid, but we obtain it by polygonal approximations. We divide the parameter interval into alpha beta into n intervals of equal width, delta t. So if t naught, t sub 1, t sub 2, all the way out to t sub n are endpoints of the subintervals, then x sub I equals to f of t and y sub I equals to g of t are coordinates of the point p sub I, which is x sub I, comma, y sub I. If I can add a little more explanation to all of this. So remember that if we have a parametric equation defined as x goes, f is defined by some, x is defined by some f of t, and y is defined by some g of t equation, some parametric equation, then there is this other variable t that we have to think about. So let's draw a number line to represent t. And t could be anywhere. It doesn't necessarily have to be at 0, but let's just have a place to identify 0. So here's 0, here's 1, and so on. It goes that way. And then over here we have -1 and -2 and so on that way. Okay, so then when you choose a value of t, any random value of t, I'm just going to put a dot on it for now. Say this dot, some t value right there. Then you go over and you plug it into your f of t function, and that's going to result in some x value. So there's going to be some other axis over here. That's the x-axis. And so that t will represent some x value over here. And then you take that t value and you plug it into your equation for g of t. And that'll give you some value along the y-axis direction. And then that'll result in some other value over there. Okay, so let's put some more detail on this. So let's say that the t-axis is listed as some starting value alpha to some ending value beta, and that t sub alpha corresponds to some value over here, which is going to be x equals to f of alpha. And this will also correspond to some starting value in x, which we're just calling a. And then there will be some corresponding value in x. Now, I don't want to make it seem like they're exactly symmetrically the same, so I'm just going to move it over a little bit. Let's say x ends over here. And so this is going to be some value b, which is the result of plugging in f of beta, right? Beta into the f function, which results in a b value. So t will range from alpha to beta, whereas x will range from a to b. Okay, so now we're going to take this interval from alpha to beta and we're going to break it up into n sub-intervals such that the first one over here, let's continue with green. The first one becomes t sub naught is this alpha value, it's the starting value. And then it ranges all the way out here to this last one, t sub n, which is the beta value. And then somewhere in the middle, there will be an ith one. So let's say that this dot right here is the ith one. So this becomes t sub I. And then right before it, and these intervals are supposed to be small, but I'm going to do it really big so we can see it. The one right before it was t sub I minus 1. And so we have this interval that changes right here. This is the change. This is the change delta t sub I. The change in the ith interval. And then that's going to correspond to some value along the x-axis. So maybe this point right here will correspond to f of t sub I, which is going to be the x sub ith value right in here. And then again, right before it, really small close up to it, x sub ith value is equal to this thing. And then right next to it, really close up to it, will be the, I'm going to put it above it here, the x sub I minus 1 value, which is equal to f of t sub I minus 1. When you plug in the t sub I minus 1, this guy will map to a value right in there, and this guy will map to a value right in there. Let's get messy, so I'm going to erase those red circles. Okay, and so now we have a change, this guy right here, which will be the change in the x sub I value. This guy will be the delta x sub I value. And likewise, we have a corresponding change in the y-axis direction. So this will be the point y sub I, which becomes g evaluated at t sub I. And then somewhere around over here would be maybe y sub I minus 1, which is g of t sub I minus 1. And again, we end up with a little change along the y-axis direction. And so this is what we like to think of as delta y sub I. Okay, so there's a change in the t direction here. As t ranges from t sub I minus 1 to t sub I, then there'll be a little change in the x and there'll be a little change in the y. For a particular point, if we let t equal t sub I, so when we have when t equals t sub I, then we have the ordered pair x sub I comma y sub I that come as the result of plugging in these values, right? We plug in the t sub I value, we get a corresponding x sub I value here, and then a corresponding y sub I value there. The x sub I and the y sub I correspond to this point, and then that in turn corresponds to this point right there, the p sub I value. So this corresponds to that point right there. All right, let's read this again, and hopefully it'll make more sense now. So we divide the parameter into the interval alpha beta into n subintervals. So t is this interval from alpha to beta, and we divide it into n subintervals, of equal width delta t, with t sub naught being the first one equal to alpha, t sub 1, t sub naught, dot, 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 t sub n being the last one equal to beta, are the endpoints of the subintervals, where x sub I equals to f of t sub I. Okay, x sub I equals to f of t sub I, we have that, and y sub I equals to g of t sub I. X sub I, f of t sub I, that's this point, and y sub I equal to g of t sub I, that's this point right over here, are the coordinates of p sub I, x sub I, comma y sub I, so are the coordinates of this point right there, that lie on the curve C, and the polygonal path, which with vertices p sub 1, p sub naught, p sub 1, right? So we're creating a method to define all these individual dots right here. And then what we can do is we can connect them and find these straight lines that connect those dots. So the straight line that connects the point p sub I minus 1 and the point p sub I is going to be this red line right there, which is defined by this. That's what this means. This represents the length of the secant line that connects these 2 points together. And then what we want to do is we want to add them all together. Remember, we've broken up our segment t into n subintervals. That means there's going to be n straight lines. This picture only shows 10 of them. So if we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, there's 10 straight red lines. So if we find the length of all those individual red lines and we add them together, that becomes our first approximation for the blue curvature C. And then if we want a better approximation, we do 100 dots, 100 lines, maybe 1,000, how about 10,000, how about 1,000,000? We want to let that get bigger and bigger and bigger. And you can see that as we make it bigger and bigger and bigger, as we increase the number of subintervals, we get more red lines. And then as we increase that, we get a better and better approximation. If we let that go out to infinity, then at infinity, we'll have the exact length of the curvature. Right? So that's what this is saying. The length of the curvature is equal to the limit as n goes to infinity of the Riemann sum as I goes from 1 to n of the lengths between p sub I minus 1 to p sub I. Okay, so now by the mean value theorem, when applied to f on the interval ti to t sub I minus 1 to t sub I, this gives a number t sub I star on the interval t sub I minus 1 to t sub I such that this is true, the mean value theorem. Now I like to remember it this way. To me it makes more sense to remember it in the other direction. I like to think about it as f prime of t sub I star is equal to f of t sub I minus f of t sub I minus 1 divided by t sub I minus t sub I minus 1. Right? All I did is divide both sides by this, and that's how I like to think about it. Remember, by the mean value theorem, what the mean value theorem tells us is that if we have a function that's continuous on a closed interval, what we could do is take the two endpoints on the closed interval and connect them through a secant line, find the slope of that secant line, and there is at least one point t sub I star within that interval such that f prime of t sub I star is equal to the slope of that tangent line. All right, really briefly, what I just said was this. If we have some function like this defined on a closed interval, so here we have some value here, a and f of a, and over here b and some f of b that traces over here. Okay, so if we think about the secant line that connects the closed endpoints like this, and think about the line that connects them like that, if we find the slope of that, then there must be at least one value somewhere between a and b. Before we used to call it c. So let's say, for example, here, there's a point c right there, c, such that the function the derivative evaluated at c is equal to the slope of the secant line that connects the two endpoints. And the slope of the secant line that connects the two endpoints is the change in y, which would be f of b over f of a, f of b minus f of a. That's the change in y, divided by b minus a. Right? So that's the mean value theorem before. And so we're applying that to this. We're saying that as t changes in this interval here, as we make changes in t, that'll have a corresponding change along the x-axis. So as long as the x variable is continuous on a closed interval, then the mean value theorem applies. There must be at least one, maybe more than one, but there is at least one value t sub I star in here. So somewhere in here, there will be a t sub I star value, such that this is true, that there's an average change, right? The mean change, the change of the whole thing is evaluated at some point. There's at least one point in here where we take the derivative, evaluate at t sub I star, and it'll be equal to the mean of the two endpoints of this, right? Okay, so that's what this is saying. And so now remember that this is the result of plugging our t sub I into the f function. This is the change in x, f of t sub I minus f of t sub I minus 1. This represents the change, so this guy is this guy, f of t sub I minus f of t sub I minus 1. That's the change in the x sub I direction. And likewise over here, this is the change in t. So now we have that this statement equals this. Change in x sub I equals to f prime of t sub I star f of t. Okay, how is that useful? Okay, so let's keep going. Likewise, we can do the same thing with the y function. So similarly, we can apply it to the g function. The mean value theorem says that there must be some t sub I double star in that interval such that the exact same thing is true. The change in y sub I is equal to g prime t sub I double star delta t. Now, the reason we have two stars is because they don't necessarily equal the same number. So going back to my little drawing over here, there was some value t sub I single star that worked for the x, right, such that f prime of t sub I is equal to this thing here. But, you know, when we look at the y, there might be some other one, not necessarily t sub I star, some other value. Let's use this red one, okay. There might be some other value, t sub I double star, that's also in here somewhere, not necessarily the same value, such that it works, t sub I double star works for this one. And so we'll say that there is some place such that g prime of t sub I double star is equal to the average change in this. So we'll end up with g of t sub I minus g of t sub I minus 1 all over t sub I minus t sub I minus 1. Good, I know it's getting really messy here. So let's squeeze this over here. G prime of t sub I is equal to the change in the y sub I divided by the change in the t. And we already have this guy for the change in x, so we can bring them both together in this equation over here. So the change of y sub I equals to g prime t sub I double star delta t. And so therefore, the length of one little line segment, this represents the length of the line segment that connects p sub I minus 1 and p sub I. Okay, we can use Pythagorean theorem for this. We used this back in chapter 8. So this is equal to the change in the x sub I squared plus the change in the y sub I squared. But we just established a new formula for the x sub I star. So that means that this is equal to this, and this is equal to this. And then we can square them. Notice that we end up with delta t squared plus, and then over here there's another term of delta t squared. We can factor out the delta t squares, and then it's inside the root. We can pull it on the outside of the root, and we end up with just the delta t. And so we end up with this, the square root of f prime of t sub I star squared plus g prime of t sub I double star squared. And so the limit L, the whole length of the curvature L is equal to the limit as n goes to infinity of this Riemann sum, right? So this was just the length of one little segment, but now if we add up all n segments and then we apply the limit as n goes to infinity, then we'll get the exact value L. Okay, so this sum right here resembles a Riemann sum for this function. It's similar to this function here, except notice that this t sub I star and t sub I double star are not necessarily the same number. So it's not exactly the Riemann sum because t sub I star doesn't necessarily have to be equal to t sub I double star in general. Nevertheless, remember that I drew them kind of big, but these intervals are supposed to be kind of small. So the change, the delta, the change in t sub I, this is supposed to be a really small interval. And even though the t sub I single star, the blue one, and the t sub I double star, the red one, they're not necessarily the same number, as this interval gets really, really, really small, as n goes to infinity, the intervals get infinitely small, and that squeezes these two numbers together to become practically the same number. So there's some good math out there that will show us that it actually works out just fine. We're not going to cover that in here, so we'll just assume that it's fine. So nevertheless, if f prime and g prime are continuous, it can be shown, that's code for, it's too hard for this class, but we're just going to accept it be true, that the limit in 4 is the same as t sub I star and t sub I double star being equal. So finally, we arrive at our formula. The length of the curvature is equal to the integral from alpha to beta of the square root of f prime of t squared plus g prime of t squared dt. Okay, and so here is our formal theorem. Theorem 5. If a curve C is described in the parametric equations x equals to f of t and y equals to g of t as t ranges from alpha to beta, where f prime and g prime are continuous on alpha beta, and C is traversed exactly once as t increases from alpha to beta, then the length of C is given by this integral, the integral from alpha to beta of the square root of dx dt squared plus dy dt squared dt. Okay, the key in this, though, is to make sure that when you set up your integral, that this is true. F prime and g prime are continuous on alpha beta, and that C is traversed exactly once. So remember that parametric equations allow you to double back and retrace a particular image. But if you want a length of a curve, we got to make sure that is not the case, that we're not retracing it more than once. So it needs to go exactly once through that space. We'll see an example in a second. Okay, so I know that was a lot. Let me zoom out and capture all of this. Okay, so it wasn't exactly a formal, rigorous proof, but just kind of walk through the explanation. I hope you were able to follow for the most part, but I do realize this is a little intense. Remember that for our class, I don't expect you guys to prove these things at this point. I hope that you got something out of seeing this sort of explanation so that down the line, if you move on to more advanced math class, at some point you might run into a more rigorous explanation and proof of this concept. And so now you have an initial rough understanding of it, even if we didn't go through the little minutia of it all. But the point is, we have a nice formula, a nice theorem, and the theorem is actually not too bad. So let's run into an example where we apply it, and you'll see that it's actually a pretty straightforward equation to work with. Just like in chapter 8.1, when we first went through the length of a curve or length of an arc, it's a very formulaic process, right? Take the derivative, add 1, square rooted, find the integral. Similar here, we're going to take the derivative of the f function with respect to t, square it, the derivative of the g function with respect to t, then square it, add them together, root the whole thing. You'll see that something works out nicely. The only thing we have to be careful of is about this part right here, to pick our alpha beta values so that we don't retrace our curve. Okay, all right, so let's jump into an example. Okay, find the exact length of the curve, x equals to 3 cosine of t minus cosine of 3t, and y equals to 3 sine of t minus sine of 3t, as t ranges from 0 to pi. All right, the first thing I want to do is graph this on Desmos and get a good sense of what this curvature looks like, and reconfirm that the x variable is not retracing itself on the range as t goes from 0 to pi. Okay, so over onto Desmos. Okay, so we have 3 cosine of t minus cosine 3t, comma 3 sine of t minus sine of 3t. So by default, Desmos allows t to go from 0 to 1. Let's just put a big number here, see what the whole picture looks like. Negative 10 to 10, for example, looks like we start to retrace it. And we can double check that by rewriting this with a variable instead of t. Let's make it a constant a as a slider. Turns this to a, turns this to a, turn this guy to a. Okay, there you can see. All right, so the little dot here, let me zoom in. So here's my image. And you can see that that little black dot just retraces more than once this whole thing. Okay, so we were given a specific range. It was from 0 to pi. So let's go starting at 0. Here is from 0 to pi. So you just get that part there. So this little guy there starts there, and there we go. So it starts there at t equals to 0, and it goes all the way out to pi, and it retraces that little purple part. So just in that little segment, there is no retracing. And when a equals to 0, we get the point 2 comma 0, which is this one here. Let me type that out. This is the point 2 comma 0. Label it right there. And when a equals to pi, we get the point negative 2 comma 0. Negative 2 comma 0. Label it, and let's change the color. Let's make them red dots at the end. There we go, there. Okay, so we want the length of this purple curvature from this point to this point. Okay, so we've already established that it does not retrace itself in this little range of t, so let's set up our integral. So we know we're going to need the derivatives, so we need the derivative with respect to t of the f of t, right? So this is x equals to f of t. This is f of t right here. F of t equals to 3 cosine of t minus cosine 3t. So I need the derivative of f prime of t. So f prime of t is equal to the derivative with respect to the letter t on cosine, oops, 3 cosine. 3 cosine of t minus cosine 3t. So this is going to be f prime of t is equal to 3, the derivative of cosine is negative sine of t, minus the derivative of cosine is going to be negative sine, so negative sine of 3t. So f prime of t is going to be equal to negative 3 sine of t plus sine of 3t. Okay. Likewise, this equation here is the g of t. So this is y equals to g of t. So g of t is equal to 3 sine of t minus sine of 3t. So when I find its derivative, g prime of t is equal to the derivative with respect to the variable t on 3 sine of t minus sine of 3t. So this derivative will be equal to 3 cosine of t minus, oh, I forgot the chain rule. This is sine, this is a times the derivative with respect to t on 3t. So we'll have an extra term of 3 from here. Whoops. So this would be f prime of t is equal to 3 minus 3 sine of t. And then the derivative of 3t is just going to be 3, so another plus 3 sine of 3t. And then over here, likewise, we're going to end up with an extra term of t, so this will be equal to cosine of 3t times the derivative with respect to t on the inside part using our chain rule. There'll be an extra derivative of 3t, so an extra term of 3 comes from there. So this would be 3 cosine of t minus 3 cosine of 3t. Okay, so I found my f prime and my g prime, and remember our formula is to square these now and to add them together. So we're working with okay, so now we're working with this equation. We want to take this thing squared, add it to this thing squared. So we're going to have f prime of t squared plus the g prime of t squared. You want to add them together, and then you want to square root the whole thing. And then that's what we want to integrate. So this is going to become minus 3 sine of t plus 3 sine of 3t parentheses squared plus, now it's 3 cosine of t minus 3 cosine of 3t parentheses squared. And then again, the whole thing is rooted, so I'm just going to raise it to the power of 1/2. Okay, so foiling this out, that's going to be fun. That's going to be equal to 9 sine squared t plus, minus. It's going to be minus 3 times negative 3 is going to become negative 9, negative 18 sine of t sine of 3t plus 9 sine squared of 3t. Okay, that takes care of that first one. Now the second one becomes plus 9 cosine squared t minus, again, minus 18 cosine of t times cosine of 3t, and plus 9 cosine of 3t squared. There. And then the whole thing is being raised to the power of 1/2. All right, so let's combine some stuff. Let's see, let's bring the sine t squared and the cosine t squared. Let's bring those two together out in front. Let's write that down as 9 sine squared t plus 9 cosine squared t. And then I also want to bring together the sine squared of 3, this guy, and the cosine squared of 3t. Bring those two guys together. So that becomes plus 9 sine squared 3t plus 9 cosine squared 3t. That takes care of those terms. Okay, so let's just bring the remaining terms together. There's a minus 18 sine of t sine of 3t. That takes care of this term. And then this term, minus 18 cosine of t cosine of 3t. Okay. All of that is still being raised to the power of 1/2. And now I'm going to factor out a 9, and we get a sine squared t plus cosine squared t. So 9 sine squared t plus cosine squared t. Right, once we factor out this 9. And I know that sine squared t plus cosine squared t becomes 1. So this whole term is just going to become 9. And likewise here, when I factor out a 9, I get the same thing. 9 parentheses sine squared of 3t plus cosine squared of 3t. That also becomes a 1, so that simplifies. That also becomes a 1. So this whole thing simplifies. So we end up with a 9 plus a 9. And now these two terms, let's factor out the minus 18. Minus 18. So if we factor out the minus 18, we get a plus. This becomes sine of t, sine of 3t, plus cosine of t, cosine of 3t. All of that still being raised to the power of 1/2. So this simplifies to just 9 plus 9 minus 18. And now everything's being added, so I'm just going to switch them around. Minus 18, and this becomes cosine of t, cosine of 3t, plus sine of t, sine of 3t. So hopefully that looks familiar, because that becomes one of our trig identities. Sum to product rules. Okay, so this turns into, let's see, the property tells us that this is going to be equal to cosine of t minus 3t. So we end up with 18 minus 18 cosine of t minus 3t, which then becomes minus 2t. This becomes 18 minus 18 cosine of minus 2t. The whole thing is still raised to the power of 1/2. So that I'm going to take over here as 18 minus 18 cosine of minus 2t raised to the power of 1/2. Let me zoom into here now. So I can factor out the 18s. So I get 18 parentheses 1 minus cosine of minus 2t. And the whole thing is being raised to the power of 1/2. It's still inside the root. Now if you recall, the cosine function is even. So plugging in a negative 2t is the same thing as evaluating it at positive 2t. So we can just rewrite this as 18 1 minus cosine of positive 2t raised to the power of 1/2, right, the whole thing including the 18. And now cosine of 2t, again, we have another identity. We can rewrite that as 18 parentheses 1 minus, and then cosine 2t can be written as 1 minus 2 sine squared t, the double angle formula for cosine. All of that is still inside the 1/2. And then when we distribute this minus, we end up with 18 1 minus 1 plus 2 sine squared t. Again, still inside that to the power of 1/2. The 1 and the minus 1s cancel to then just give me a 2 sine squared t. So I get 18 times 2 sine squared t. Again, still inside that power of 1/2. And so now we get 36 sine squared t raised to the power of 1/2. And keeping in mind that we are only interested in t ranging from 0 to pi for t. If we think about the sine function is always positive on 0 to pi. So if we think about a little sketch of sine, it starts here, goes up, comes down, goes like this. So just on the section that we're interested in, from 0 to pi, the sine function is always positive. So we already have a positive number, we square it and we square root it, we get back to the original number. So squaring and square rooting it just gives you back the original sine function, and because it's positive, we don't have to worry about a negative number, right? So, negative 3, if you square it and then you square root it, well, then you get the positive 3, so you have made a difference, right? So if we have a negative, we have a problem. But if we have a positive number and we square it and then we square root it, well, we just get back to the same positive number. Okay? So that's why this just becomes sine, and then the square root of 36 is just 6, so we end up with 6 sine of t. Okay, so setting up our integral, we have that the length L, the length L is equal to the integral of f prime of t squared plus g prime of t, parentheses squared, all that in a giant root, dt. And this is from 0 to pi. This is as t goes from 0 to t goes to pi. Okay, so all of this over here is this root. So this integral is going to simplify quite a bit. This is just going to become that the length L is the integral from 0 to pi on 6 sine of t dt, right? All of this is this guy, 6 sine t. Okay, so this then becomes 6 minus cosine of t evaluated from 0 to pi, which means that the length L is negative 6 times cosine of pi minus cosine of 0. And cosine of pi is equal to negative 1. And cosine of 0 is equal to positive 1. So then this turns into the L value is negative 6 minus 1, which gives you minus 2 times negative 6. So L equals to 12. And that's our answer. L equals 12. Okay, so we were given a parametric equation defined this way. X equals to 3 cosine of t minus cosine 3t. Y equals to 3 sine t minus sine 3t. And we're asked to find the exact length of the curve as t ranged from 0 to pi. Okay, so following this formula, the integral from 0 to pi on the square root of f prime of t squared plus g prime of t squared, I went ahead and found those two values first. So looking at my f of t function, I found the derivative with respect to t. That gave me this equation. The derivative with respect to t on the g function is equal to this equation. Squared them and then added them together, put them inside the root, foiled, combined, simplified, used a couple of identities. That brought me down to this guy. Again, I can further factor out the 18, use another identity, simplified it, all worked out really nicely down to this statement, the square root of 36 sine squared t. Since t is only ranging from 0 to pi, the sine function is always positive. Therefore, sine squared square rooted is just going to be positive sine t. And the square root of 36 is 6, so that just simplifies to 6 sine t. So plugging it into our integral, this whole part in here just boils down to 6 sine of t, the integral ranging from 0 to pi. And so that gives me negative 6 cosine of t, ranging from 0 to pi, and then that simplifies to 12. So this arc length here is 12 units long. Okay, and so the last topic in this section is surface areas. So in the same way as for arc lengths, we can adapt the formulas from Chapter 8, Section 2, to obtain a formula for the surface of area. So suppose that a curve C is given by a parametric equation x equals to f of t and y equals to g of t as t ranges from alpha to beta, where f prime and g prime are continuous, and g of t is greater than or equal to 0. And C is traversed exactly once as t increases from alpha to beta. If C is rotated about the x-axis, then the area of the resulting surface is given by this integral. So this should look familiar back from Chapter 8. The surface area is equal to the integral as t ranges from alpha to beta of 2 pi y, 2 pi y because we're rotating about the x-axis. And then this acts as our new ds. So it's dx dt squared plus dy dt squared, square root of the whole thing. So the general symbolic, the general symbolic formula s equals to the integral of 2 pi y ds, and s equals to the integral of 2 pi x ds from chapter 8 still work. Remember, we use this one when we're rotating about the x-axis, so we use 2 pi y, and when we're rotating about the y-axis, we use 2 pi x, and now we just need to find our ds, and so this becomes our new equation for ds. Okay, find the exact area of the surface obtained by rotating the given curve about the x-axis. So we have that x equals to a cosine cubed of theta and y equals to a sine cubed theta, as theta ranges from 0 to pi over 2. So the first thing I want to do is graph this to get a sense of what it looks like. So let's go over to Desmos. Okay, so here is the graph in Desmos. Here's the parametric equation, a cosine cubed of theta, but I had to use t because Desmos likes t for parametric equations, comma a sine cubed t, as t ranges from 0 to pi over 2. And a is just some constant, so I used it as a variable here. I can go from, I don't know, negative 10 to 10. And let's see, 0.1 here. So you can see it as a slider. You can see it as a slider to see what it would look like. So as long as a is positive, it stays on the right side. Okay, so if a is some positive constant, then this is what the graph looks like. Remember, this is the x-axis here. This is the y-axis. So we're going to rotate this about the x-axis, and you'd get something that looks like a little pointy mountain that comes this way, and we want to calculate the surface area. All right, so let's do our calculation. So we need to set up our integral. Our integral is going to be equal to the integral from 0 to pi over 2 of 2 pi y, y because it's the x-axis. We're rotating about this x-axis, so we need 2 pi y. And then we need the ds, which for us in this case will be equal to, ds is equal to dx dt squared plus dy dt squared, and then it's the square root of that whole thing. So let's figure out what this is. Dx dt, d dt of the x function is going to be a cosine cubed theta. Well, I already changed the t for the other one. Okay, so since we're using the variable theta, let's just change it all for the variable theta. Let's get rid of this thing here. Let's get rid of this thing here. And then let's get rid of this thing here. In fact, let me just start all over with this guy. So Desmos liked t, but we don't have to stick to t. We can go with theta. So this becomes theta there, theta there. Okay, so come back over here. X equals to a cosine cubed theta. So dx d theta is the derivative with respect to theta on a cosine cubed theta, which means dx d theta is equal to 3a cosine of theta squared times the derivative of the inside part using the chain rule is going to be equal to negative sine theta. And then for y, we have y equals to a sine cubed theta. dy d theta becomes d d theta of a sine cubed theta. And so dy d theta becomes 3a sine squared theta times the derivative of the inside part, which becomes cosine of theta, Okay, so we have ourselves our dx d theta. We got to square that, and then our dy d theta, squared that, add them together, and find the roots. So we can find our ds. So this is going to be 3a cosine squared theta, and then negative sign, so I'll put a minus out in front, minus sine of theta, this whole thing squared, plus now 3a sine squared theta, cosine of theta, and then this whole thing squared, and then the whole thing is inside this giant root. So ds is going to be equal to 9 cosine to the fourth, sine to the second power. So this would be 9 cosine to the power of 4 theta sine of theta squared plus, I forgot the a squared in front. There's a 9a squared, 9a squared. And same thing over here, 9a squared sine to the fourth power theta cosine squared theta, still inside this root. Okay, so we can factor out a 9a squared, leaving me cosine squared, sine squared, and sine to the fourth cosine. So we can also factor out 2 powers of cosine and 2 powers of sine. This becomes 9a squared cosine squared theta sine squared theta, parentheses, and what survives here is going to be a cosine squared theta, plus, and what survives here is a sine squared theta, still inside that root. ds equals all that. And now one of the identities we can use is cosine squared theta plus sine squared theta. This part becomes 1. And so now we just have this. And so ds is equal to 9a squared cosine squared theta sine squared theta, root of all that. Okay, so ds becomes 3a cosine of theta sine of theta. All right, so all of that was to figure out our ds. So now we can come back over here finally and continue with this integral from 0 to pi over 2. And now we're going to rewrite this as 2 pi y is equal to a sine cubed theta times my ds, which is equal to 3a cosine of theta sine of theta. Oh, and I forgot my d theta. Oops. Okay, so this is supposed to have a times d theta at the end here, times d theta, d theta, d theta, d theta, d theta. So there's a d theta here, times d theta. Okay, so then that means that this whole thing from a cosine theta sine theta to d theta, this whole thing is my ds. And this guy right here is my y. So 2 pi y ds. Okay, so now let's try and simplify this. We have a constant there, a constant there. The a is a constant as well. 3 is a constant. Okay, so a lot of constants. 2 pi, 6 pi, 6 pi a squared. 2 pi a squared, and then the integral from 0 to pi over 2. And 2 pi a, that's been taken care of. So the only thing that survives inside here is sine to the third, cosine, and sine. So we end up with sine to the power 4 theta, cosine of theta, d theta. And so now we can do a u substitution. Let u equal to sine of theta. Therefore, du is going to be equal to cosine of theta d theta, and that lets me do this substitution of u to the power of 4, and we want to integrate that. And now when theta equals to 0, we get u equal to 0, and when theta equals to pi over 2, sine of pi over 2 is 1, so u goes to 1. And this is just going to be my du. So evaluating this gives me that this is just going to be equal to, I'll bring down the constants, 6 pi a squared. This leads to 6 pi a squared, and then this is going to be 1/5 u to the power of 5, evaluated from 0 to 1, which then becomes 6 pi a squared over 5. And this is going to be 1 to the 5th power minus 0 to the 5th power, which is just going to become 1. And so we end up with our final answer of 6 pi a squared all over 5. Cool, and that'll be our answer. Let me see if I can try and sketch this out. Okay, I've typed this all into Desmos. So here we have our parametric equation described this way. X sub 1, this is the function in x is a cosine of u cubed, and y, the y variable, is a sine cubed. That's the order in which they were. Yeah, okay. So, and then we have the variable a out in front. So we can see what this looks like here. If we look at it from sort of the top bottom, we see that it looks like this. And then we want to rotate this about the x variable. So if I put it back into 3D mode, I've already wrote this little code down here will help us rotate this. So if I rotate this guy like so, you see how it rotates. It rotates about the x-axis, right? So let's make this I don't know, bigger. Let's make it 50, and then have that there. So you see how it's rotating, rotating, rotating toward it. So we want to kind of envision what happens as we generate that whole shape of it rotating. So to do that, let's change this over here. Let's get rid of this guy. And so there, it looks like this. Let me see if I can zoom in a little bit. So it goes like that. And you can see that it looks like this. Okay, and so we have an equation that describes the surface area of this. Right? So if we just had this very thin layer covering it, see how it's hollow underneath, because we're just thinking about the surface area. So if we had to paint this on the outside, for instance, how much paint we'd have to use, the surface area of this shape, hollow on the inside.